The theme of Isaac Newton's alchemy has seriously occupied scholars for the last half century. The subject was briefly introduced in David Brewster's 1855 Memoirs of Newton's Life, and then treated in occasional articles by various subsequent scholars. But with the publication of Betty Jo Dobbs's pioneering Foundations of Newton's Alchemy in 1975, and Richard Westfall's Never at Rest in 1980, the first sustained attempts were made to determine the motives behind Newton's involvement in the aurific art. For Dobbs, whose views evolved into the positions expressed in her final book on the subject, the 1991 Janus Faces of Genius, Newton's alchemy was part and parcel of his unorthodox Christianity. Heavily influenced by Carl Jung, Dobbs believed that Newton was trying to use alchemy to obtain an experiential understanding of divinity, in which the philosophical Mercury of the alchemist could be identified with, or at least seen as an analog of Jesus. Westfall, on the other hand, believed that Newton turned to alchemy as part of his rebellion against Cartesian mechanism, and that the English philosopher even derived his belief in force at a distance from his chemical studies. Hence, for Westfall, it was only natural that Newton would abandon alchemy in the 1690s after he had written his masterpiece on gravitation, the Principia. It's not my aim to dispute the views of Dobbs and Westfall here, since I've addressed their positions at length, both in my recent book, Newton the Alchemist, and in the Cambridge Companion to Newton. Suffice it to say that neither of their arguments withstand the weight of the evidence when subjected to serious scrutiny. Rather than repeating my arguments here, I'd like to suggest some alternative motives for Newton's alchemical endeavor, which occupied some 40 years of his life and only faded in his 60s when he had ceased his own laboratory experimentation as a whole. It's in this sense that I intend to examine the principles behind his practice, namely the guiding principles or motives behind Newton's decades-long involvement with alchemy. In my view, the attraction of alchemy for Newton was multifaceted, complex, and evolving, as befits a pursuit in which one is involved from youth to late maturity. As I argued in Newton the Alchemist, the celebrated scientist's first exposure to chemistry, however dilute, may be found in the books of secrets or natural magic that he studied as an adolescent. For example, we know of Newton's exposure to John Bates' Mysteries of Nature and Art, which contains material on pigment and various so-called vulgar chemical examples. We know of this from the Pierpont Morgan manuscript of Newton's that was composed between 1659 and 1661. Similarly, the Pierpont Morgan manuscript records extracts from John Wilkins' Mathematical Magic. Newton's extracts contain no mathematics, however. They focus exclusively on chemical means of attaining the marvels of perpetual motion and eternally burning lamps. As Wilkins makes clear, his topic is thaumato-poieticae, or thaumaturgy, the production of wonders. And this seems to have been a topic of driving interest for the young Newton. One might suppose that this was a mere boyhood interest and that Newton quickly passed to the more serious mechanical philosophy upon matriculating at Cambridge in 1661. This was, in fact, the position of Westfall, who argued that Newton's first major exposure to chemistry occurred through Robert Boyle, and that it only took place after Newton had begun his study of Descartes. But Westfall was unaware of the fact that Newton had already copied the comprehensive chemical glossary now found in the Schaffner collection at the University of Chicago before his exposure to Boyle's work. This so-called treatise of chemistry was not an original Newtonian composition, as Westfall thought, but rather a copy that Newton made in the 1660s from an existing source. Very likely, Newton's interest in chemistry at this point had nothing at all to do with the mechanical philosophy. Instead, I surmise that it was a continuation of his early interest in the wonders of art and nature that he acquired from authors such as Bate and Wilkins. Moreover, if one examines Newton's late alchemical manuscripts, such as the treatise Praxis that he composed in the 1690s, the same focus on thaumaturgy seems to be present. Consider the following passage from Praxis. Thus you may multiply each stone 4 times and no more, for they will become oils shining in the dark and fit for magical uses. You may ferment them with gold and silver by keeping the stone and metal in fusion together for a day and then project upon metals. Here one can see that the Thaumato-Poieticae of Wilkins and Bate was still an attraction, even in Newton's maturity. But by no means was it the sole attraction of alchemy for Newton. As the adolescent matured, he began to see how chemical knowledge could be applied to experimental natural philosophy as a whole. His early optical discoveries, for example, employed the principle of analysis followed by synthesis, or as Newton calls it, redintegration of white light. Although the discovery that white light could be broken down into its spectral rays of fixed refrangibility by means of a prism and then reassembled by means of a lens was Newton's own original discovery, his terminology betrays a debt to Robert Boyle. Only 5 years or so before Newton's discovery, Boyle had published his treatise on the redintegration of niter, or saltpeter, which argued that saltpeter can be broken down into its components and then reassembled like a dismantled watch to regain the original saltpeter. Such arguments from paired analysis and synthesis were virtually non-existent in natural philosophy before Boyle, although they have a history in alchemy. This fact, in tandem with Newton's adoption of Boyle's unusual terminology, has led me to argue that Newton's use of paired analysis and synthesis is partly a carryover from chemistry. But there's plenty of other evidence that Newton was transferring alchemical material and using it in natural philosophy as well. The first English edition of the Optics, appearing in 1704, connected sulfur, inflammability, and refraction in a highly significant way. Newton observed that inflammable bodies exhibited considerably more refraction than non-combustible materials of a similar density. In order to reveal this fact, he even constructed a table relating the refractive powers and densities of 22 different materials, thus deriving the refractive power of each substance, as he says, in respect of its density. By the compositional reasoning descending from Paracelsus and other chemists, substances that burned contained the principle sulfur, which was released during the process of combustion. On the basis of this chemical theory, then, Newton argued for a correlation between the amount of sulfur in a given body and its ability to refract light. Newton's faith in the reality of the chemical sulfur principle led him to conclude that camphor, olive oil, turpentine, and amber were all, as he says, fat, sulfurous, unctuous bodies. And even diamonds, which Newton knew to be combustible at high temperatures, were probably, to use his words, an unctuous substance, coagulated. A final obvious area where Newton's natural philosophy and alchemy intersected can be seen in his famous treatment of elective affinity in the Optics. Recognizing the dominant position of Newtonian science in the siècle des Lumières, numerous 20th century historians and even a number of important Enlightenment figures themselves viewed Newton's Query 31 as the origination point of the great vogue for affinity tables in the 18th century. These graphic displays of solutions and precipitations typically embodied the principle of elective affinity or elective attraction, according to which one material has a greater tendency to combine with another than with a third party. Consequently, if the third material is already combined with the first, it'll be displaced by the introduction of the second. Query 23 of Newton's 1706 Opticae and query 31 of the 1717 Optics had famously spelled out the same principle with multiple examples such as the following, which describes successive dissolutions and displacements of materials dissolved in nitric acid. So Newton says, and so when a solution of iron in aqua fortis dissolves the lapis calaminaris and lets go the iron, or a solution of copper dissolves iron immersed in it and lets go the copper, or a solution of silver dissolves copper and lets go the silver, or a solution of mercury in aqua fortis being poured upon iron, copper, tin, or lead dissolves the metal and lets go the mercury, does not this argue that the acid particles of the aqua fortis are attracted more strongly by the lapis calaminaris than by iron, and more strongly by iron than by copper, and more strongly by copper than by silver, and more strongly by iron, copper, tin, and lead than by mercury? In reality, the originator of the first graphic affinity table, Etienne Geoffroy, may have composed it quite independently of Newton's optics. But here I'm concerned with the interplay of natural philosophy and alchemy in Newton's work, not in priority claims. Consider, for example, Newton's alchemical treatise that I call the Opera Floralegium, composed between the late 1680s and mid-1690s. Here one can clearly see the influence of the Polish alchemist Michael Syndevogius. Newton's text contains an analysis of Syndevogius's 1604 Novum Lumen Chemicum in terms of solutions and precipitations of metals. In tract 9 of his book, Syndevogius had used the geocentric system as an illustration of the fact that the planetary powers descend to the earth but do not ascend from it. The same thing is true, he says, of the metals that correspond to the individual planets. Hence, a superior planet like Mars sends its virtues down to its inferior counterpart, Venus, and so iron can be transmuted to copper, but not vice versa. By the same logic, Jupiter or tin becomes Mercury or Quicksilver, and Saturn, that is lead, becomes Luna, that is silver. In the course of expounding this passage, Newton explicitly links it to the precipitation of metals dissolved in an acid. He says, Venus mates with Mars, Luna with Saturn, and Mercury with Jove, because an acid spirit deserts Venus so that it may enter Mars, and deserts Luna so that it may penetrate Saturn, and deserts Mercury so that it may work on Jove. There's no reason to think that Newton initially read this as a single series of reactions instead of as paired examples. But the important thing is that he clearly did identify Syndevogius's series of so-called transmutations as solutions and precipitations. The so-called acid spirit of the passage refers to a corrosive such as nitric acid, which indeed deserts copper in order to attack iron put in a solution of copper dissolved in the acid. It's likely that he read similar passages in other crucipoetic writers in the same way. Some alchemical authors, for example, the American chemist Irenaeus Philalethes or George Starkey, explicitly presented such transmutations as a single series. It's therefore likely that Newton's own crucipoetic research and experimentation, coupled with his wide chemical reading, provided the first impetus to the lists of combinations and displacements characterizing the 1706 Opticae, query 23, and the 1717, query 31 in the Optics. The three examples that I've given, analysis followed by redintegration, linkage of refraction to the chemical sulfur principle, and the concept of elective affinity, all demonstrate the bleed through from Newton's chemistry to his natural philosophy as a whole. I could supplement this with many other examples drawn from Newton's treatises written in the 1670s, such as Of Nature's Obvious Laws and Processes in Vegetation, or The Hypothesis of Light. This evidence strongly supports my view that one of Newton's motivations for studying alchemy was to extract natural secrets from it and put them to use in natural philosophy. So we have found two motivations thus far: the desire to produce marvels and the quest for natural knowledge acquired by experiment. What other guiding principles drove Newton's alchemical work? Well, one obvious place to look lies in the realm of medicine. Chemical medicine, or iatrochemistry, had become a cause célèbre in Europe after the death of Paracelsus in 1541. Moreover, it was commonly believed that the philosopher's stone itself was an elixir with Panacean properties. Yet both Westfall and Dobbs are almost entirely silent on this matter. If one goes looking for medicine in the 900 pages of Westfall's magisterial Newton biography, Never at Rest, for example, one is likely to fall only on his paragraph describing Newton's preparation and use of Lucatello's Balsam. This was a popular wound ointment in 17th century England, made from turpentine, the best damask rosewater, beeswax, olive oil, and sack, flavored with a pinch of red sandalwood and a dash of oil of St. John's wort. According to his Trinity roommate, John Wickens, Newton would periodically melt a quarter of a pint of this unctuous mass and drink it for internal ailments as well. Beyond that, Westfall says hardly a word about Newton and medicine, never mind chemical medicine, despite the fact that his biography contains two substantial chapters in which alchemy is extensively covered. The impression that Newton was uninterested in chymiatria or medical alchemy is hardly altered by a consultation of Dobbs's work. The Foundations of Newton's Alchemy provides good summary descriptions of chemical medicine as practiced by various members of the Hartley Circle, including Boyle, but it's virtually silent on any interest that Newton might have had in the subject. This silence is rather odd, given that Newton's main chemical laboratory notebook, Cambridge Additional Manuscript 3975, found in the Portsmouth collection at Cambridge University Library, contains extensive reading notes from iatrochemical sources. This is the first page of the manuscript. Within the covers of this 174 folio manuscript, Newton compiled an extensive commonplace collection consisting of 64 pages on Helmontian chymiatria, which he entitled The Medical Virtues of Saline and Other Preparations. The collection is derived exclusively from Boyle and George Starkey, but it's not Starkey's crusopoetic works written under the pseudonym of Irenaeus Philalethes that Newton digested here. Rather, it's Starkey's 1658 defense of Helmontian iatrochemistry, pyrotechny asserted and illustrated. Newton originally planned for this medical collection to extend over 25 folios of CUL Ad 3975, but then he found that he needed another 6.5 folios in order to accommodate all that his sources had to tell him about volatile salts and alkalis. Hence, he had to jump to another point in the bound manuscript when he ran out of space in the 25 folios that he had originally allotted to the topic of Helmontian medicine. Some 2 folios after the end of the commonplacing that I've been discussing, one also encounters a set of chymiatric recipes in Latin. These extend from folios 134 recto through 135 verso, and they describe cures for a variety of ailments ranging from stomach pain to breast cancer. Remarkably, 4 of the 9 recipes are intended for diseases specific to women, 1 for hysteria, 1 for easing the pain of labor, and 2 for breast cancer. The source of these recipes is unclear, but they are definitely early modern, as they cite New World medicaments such as contraierva and Virginia snake root. Moreover, one of them actually refers to Hadrianus Munzicht, a court physician of Adolf Friedrich, Duke of Mecklenburg-Schwerin. Unfortunately, it's unclear whether the reference to Munzicht comes from a source copied by Newton that cited Munzicht, from Munzicht himself as copied by Newton, or is instead a reference inserted by Newton into a passage copied from another author. I've not been able to find any of these Latin recipes in Munzicht's famous Thesaurus et Armamentarium Medico Chemicum of 1631, despite the fact that Newton owned the 1651 Rouen edition and even quotes it in his papers. Hence, for now, these 4 pages of iatrochemical recipes remain unidentified. At any rate, these unidentified recipes are not Hillmontian in the obvious way that Starkey's were, and they reflect a different genre in early modern chymiatria, namely the massive collections of medico-chemical particularia that swelled the libraries of 16th and 17th century physicians. Such pharmacological collections were often quite remote from crusopoetic concerns, even if their authors were otherwise believers in the aurific art or even transmutational practitioners. That Newton's reading included this medical genre appears not only from the Latin recipes in CUL Ad 3975, but also from occasional references in his papers to Johann Schröder, a well-known physician of Frankfurt am Main, whose Pharmacopoeia Medico-Chymica was first published in 1641. Savity Lot 96, a manuscript now in private possession, contains 3 closely written pages taken from Schröder's Pharmacopoeia in what appears to be Newton's early hand. If you look at the top of the page, the notes consist of entries for a number of medical and chymiatric terms, such as alcohol, bolus, collyrium, colophonia confecta, crocus, electuarium, eulep, and laudanum. These entries are followed by mineralogical and metallurgical information, also taken from Schröder. Hence, the manuscript provides further evidence that Newton was reading broadly in the medico-chemical literature, not just in crusopoetic authors. In my remaining time, I'd like to pursue the issue of Newton's medical interests and their relation to chemistry a bit further. A particularly cogent case can be found in Newton's relationship with Nicolas Fatio de Douillet, the young Genevan mathematician who established a working relationship with the natural philosopher after his arrival in England in 1687. In addition to a talent for mathematics, Fatio also had a strong interest in alchemy, or perhaps he developed it in England. The 2 men were already discussing alchemical topics in 1689, as shown in a letter from October the 10th, where Newton criticizes Boyle's openness on the topic. Our next surviving exchange from Fatio to Newton consists of a dramatic letter dated September the 17th, 1692, in which Fatio reports that he's contracted what he calls a grievous cold and fears for his life. The letter is of interest for the detailed medical information that it contains, presented in an almost clinical style. Fatio says that he experienced a sensation like, as he says, the breaking of an ulcer or vomica in the undermost part of the left lobe of his lungs. He speaks of lurching forward involuntarily on a momentaneous sense of something bigger than my fist moving when the abscess seemed to break. He follows this with the information that his pulse is now good, but that he is feverish. A medication called Imperial Powders has apparently proved ineffectual, though in a subsequent exchange, Fatio would change his mind about that. Within a week, Fatio's health had dramatically improved. The Imperial Powders had proven to be an effective sudorific, and the only other sign of their activity had been that they also raised pimples on Fatio's lips. Fatio seems to have interpreted the pimples as a good sign. Perhaps their formation meant that the peccant matter of the disease was being drawn forth. Meanwhile, his fear of a pulmonary abscess had turned out to be unfounded, though, he says, a foemus of an exceeding sharp and troublesome matter, presumably meaning a discharge of phlegm, had developed, accompanied by a severe headache. It's perhaps significant that the Imperial Powders were among some items that Newton would purchase from Fatio in the following year for the extremely handsome sum of 15 pounds. What were these Imperial Powders in which Fatio and apparently Newton placed so much faith? There were a number of so-called imperial medicines in circulation in the 17th century, and without further information, one cannot be absolutely sure. One possible candidate, however, is found in the popular Thesaurus and Armamentarium of Munzicht that I mentioned. In this text, one finds a recipe for imperial bezoartic powder that contains elk and staghorn that have been, quote, calcined sphagerically, end quote, along with bole, bezor, terra sigillata, flowers of sulfur, unicorn horn, magistery of oriental pearls, red flowers, native cinnabar, the bone from a stag's heart, and amber. While the reference to spagyric calcination qualifies the compound medicine as a chemical remedy, it is in most other respects very similar to the Gloria Inestimabilis of pseudo-Aristotle, made famous by Roger Bacon, and to numerous other medieval medicaments that employed expensive and exotic ingredients. At any rate, Munzicht recommends it as a diaphoretic for use in acute fevers, which acts by removing vicious and venomous humors through sweating. This, of course, was the very action that Fatio had attributed to his imperial powders, which might suggest that they were related to Munzicht's. Whether Fatio's imperial powders were identical to Munzicht's or not, his literary and material exchange with Newton suggests that the two men were looking for sophisticated chemical medicines. For Newton, we already know this to have been the case from his chymiatric entries in CUL additional 3975. A further look at the continuing correspondence between the two men reveals how this desire for effective medicinal particulars developed into a full-blown quest for the great elixir itself, the lapis philosophorum, as early as spring 1693. The letters tell a fascinating story, and one that has serious implication for Newton's research, as reflected in his experimental records and in his late alchemical manuscript, Three Mysterious Fires. The first evidence appears in an often quoted epistle of May the 4th, in which Fatio informs Newton of alchemical marvels produced by a new acquaintance of his in London. Fatio's anonymous chemical friend has succeeded in producing an animated mercury that leads to the growth of metallic trees in a laboratory vessel. The letter goes on to describe the activities of this philosophical mercury in its vessel, but that's less important for us than Fatio's further comments. The next scene in the unfolding drama of the Newton-Fatio collaboration occurs in a letter written by the young aspirant and sent from London on May the 18th. Fatio begins with news that Newton had already heard. The former's mother has died, and he's been trying to sort out his inheritance. Also, as a younger son with sisters on whom dowries had to be settled, Fatio has found that his allocation is inadequate. Thus, he's casting about for a way to make a living. One possibility would be to obtain a medical degree and to employ chemical medicines as a source of income. Here, the unnamed friend of Fatio re-enters the picture. The friend has had wonderful successes with his alchemical medicine, giving it to more than 10,000 patients, sometimes as many as 500 in a single day. Moreover, it's cheap to prepare. In fact, the anonymous friend has been treating Fatio himself with a medicine which, Fatio says, cures the smallpox radically and frees the body from black bile. The young Genevan reports that a second dose of the marvelous medicine brought up 2 or 3 pints of a black-green bile, which of course he takes to be a very propitious sign. Moreover, the anonymous friend has offered to teach Fatio the preparation of the medicine, which requires a menstruum or dissolvent that takes 7 months to make and goes through 4 successive putrefactions. Fatio at first demurred from accepting this offer, but he's now reconsidering. The May 18th letter strongly suggests that the young Genevan wants Newton to provide backing for this project, although the letter does not specify whether this should take the form of funding, supplies, or time. The record of the Fatio-Newton collaboration proceeds no further in the printed Newton correspondence. Thanks to several recently discovered documents, however, I've been able to follow the story all the way up to November of 1693. The first of these new documents is a letter from Fatio to Newton dated August the 1st, 1693, found in the Clark Library in Los Angeles and first brought to my attention by Scott Mandelbrot. The letter again refers to Fatio's unidentified alchemical friend, but adds the additional information that he was a Francophone soldier and that he would soon have to return to Flanders, thus interrupting their alchemical work. By now, all three men were deeply involved in a project to make the marvelous menstruum described by Fatio on May the 18th. Hence, the departure of Fatio's chemical friend and teacher would be a major blow to their success. The letter also contains a substantial Latin passage from a now lost letter by Newton that Fatio has returned to him for explication, since the alchemical friend finds part of it to be bewildering. The passage turns out to be a major interpretive key that allows us to understand Newton's mature alchemical practice, as I've described in Newton the Alchemist. But for now, let's focus on the newly revealed facts that Fatio's friend was a French-speaking military man serving in Flanders. A second unpublished document, also written in the hand of Fatio, casts additional light on the likely identity of Fatio's friend. Possibly part of a letter from the Genevois to Newton, this text is found in a photocopy kept in the British Library. It consists of detailed descriptions for making lute, the clay-like material that chemists use to seal their glassware and to reduce thermal shock. For us, the important thing is not these interesting technical directions, but rather a paragraph found on the second sheet of the photocopy. It says, Monsieur de Teigny, a captain in the French regiment of Cambon, who married one Monsieur de Grancey's sister, and he was a gentleman of a good estate in France. His lands were in Poitou, about Teigny, within 3 or 4 miles of a place where they dig out some excellent antimony. Was this Monsieur de Teigny the source of the detailed instructions that Fatio gives for making lutes? Very likely he was, since it was common practice in the literature of secrets and recipes to follow the directions with their source. Moreover, the French regiment of Cambon, in which Teigny was serving, was a military unit composed of Huguenots who would serve under English rule in Flanders. The name Cambon is surely a reference to Francois Dupuy de Cambon, who commanded a Huguenot regiment under King William that was raised in 1689. Cambon died in the summer of 1693, but he was still living at the very beginning of August when Fatio indicated that his friend might have to depart for Flanders. Hence, Captain de Teigny could well be Fatio's anonymous alchemical friend. In fact, my tentative identification in Newton the Alchemist of Fatio's unnamed friend with this Captain de Teigny has recently acquired further corroboration thanks to Lavinia Madaluno's discovery of 4 draft letters from Fatio to Newton in the Universitätsbibliothek in Leiden. 3 of the letters shed additional light on the Fatio-Newton alchemical collaboration, in particular because they refer repeatedly to Fatio's soldier alchemist as the captain. But the new biographical details about Newton's collaboration with Fatio do not end here. As I pointed out in Newton the Alchemist, yet another previously unexamined document, this one in the University of Texas, shows that Fatio and Newton were communicating about chemical matters well into November 1693, thus belying Richard Westfall's supposition of a radical break between the two men by September of that year. In fact, this combined evidence casts serious doubt on the related idea that a rupture with Fatio contributed to Newton's famous derangement of the intellect or nervous breakdown of September 1693. But let's return one more time to the content of the alchemical Newton-Fatio project as revealed by their correspondence. On the basis of numerous descriptions of unusual apparatus and processes in Fatio's letter to Newton, I've been able to show elsewhere that Newton's manuscript, Three Mysterious Fires, kept at Columbia University, represents the culmination of this collaboration with Fatio and Captain Teilly. The manuscript, which devolves into a succession of fantastically complicated procedures, introduces two additional features. One of them present, that is, two additional people, figures, one of them present only in a literary faculty, the other perhaps as a fourth physical collaborator. The text begins as a commentary on the German alchemist Johann de Monte-Snyder's famous texts of the 1660s, the Commentatio de Pharmaco Catholico and Metamorphosis Planetarum. In my opinion, these are some of the most obscure alchemical texts ever written, but they were among Newton's favorites. The English commentary that comprises the beginning of Three Mysterious Fires is written in a brash and confident tone that is very different from the circumspect voice of Newton's other private alchemical notes. Nor is it like anything of Fatio's, and it betrays a deep knowledge of Monte-Snyder's work that the Genevan, that is Fatio, seems to have lacked. I therefore suggest that this section is written by an unknown Anglophone alchemist, who was possibly a fourth member of the project, initiated by Fatio, Newton, and Teilly. The English section is followed by a Latin recounting of additional, very complicated processes that may well reflect Newton's own interpretation of the information that Fatio gave him in letters and perhaps orally. They begin with the multiple repeated sublimation of metal salts that typically characterize Newton's laboratory practice, which we know from his experimental notebooks in Cambridge. Here's an English translation of the Latin. These processes are intended to lead to the marvelous menstruum described in Fatio's letters to Newton, which is now clearly identified with the mysterious elixir of Monte-Snyder's. From Newton's literary exchange with Fatio, one can therefore see a clear line of development from the commercial imperial powders that the Genevan used to cure his cold, up to the fantastically complicated protocols described in Three Mysterious Fires. The boundary between ordinary iatrochemistry and the quest for the grand elixir was porous indeed, if not entirely non-existent. Well, we can now draw this talk to a conclusion. As I've shown, Newton's long alchemical endeavor was the product of at least three distinct evolving motivations. His early interest in books of secret and natural magic soon developed into a study of alchemy for its own sake, probably deriving from a desire to produce marvelous effects. In the next stage after Newton's transcription of the glossary treatise of chemistry, he moved on to the study of Basilius Valentinus, whom I've not described here. But the intensely practical character of Newton's reading notes on Basilius suggests that his early enthusiasm for alchemy aimed at something like Wilkins' Thaumato-Poieticae, rather than the advancement of natural knowledge. This began to change in the late 1660s, however, with Newton's brilliant discoveries in optics, which were clearly linked to chemistry. Additionally, this is the time when he wrote of nature's obvious laws and processes in vegetation, which is a sustained attempt to integrate the mechanical philosophy with alchemy. Finally, we've seen the deep integration between chemistry and medicine in the minds of Newton and his co-worker of the early 1690s, Nicolas Fatio de Douillet. Their collaboration itself underwent an evolution from the quest for commercial medicines, such as Fatio's Imperial Powders, to a frenetic attempt to reproduce the obscure and exotic products described in the work of Johann de Monte-Snyder's. From all of this, we can see that there is no simple answer to the question, why did Newton practice alchemy? Still other possible motivations could also be introduced, such as the pursuit of material wealth. The man who reportedly lost at least 10,000 pounds in the South Sea bubble of 1720, and yet still managed to die with 32,000 pounds in liquid assets, cannot have been immune to the attractions of lucre. Yet, even if this may have been one of Newton's motivations, and so far I haven't found a way to prove it, I have shown in today's talk that it can only have been one factor among many, and with that, I come to a conclusion. Thank you.